Alright, this video is going to cover modularity, which is a metric used for community detection to determine how well the network partitions into modules. As a refresher, community detection is the process of partitioning a graph or network into groups of nodes such that within a group those nodes are highly connected, but across the groups there's few connections. For example, here we have a graph consisting of 15 nodes, and in this graph we've partitioned it into 3 communities, given by the different colored circles. And this structure adheres to the property I just mentioned. Within each community, they're pretty highly connected, and across communities, there's not many links. Now, there's no formal or universally accepted definition of community, but generally, this is the kind of structure that community detection methods try to find. However, a natural question is, what is the best way to partition this graph that adheres However, if we look at this example graph again, there's different ways that we could partition the nodes into different groups. So on the left-hand side, we have 3 communities. On the right-hand side, we have 2 communities. Which one of these is better? Well, it's hard to say because at this point we have no objective way of valuing the communities and no objective way of determining which one's better. We may think that the partition on the left is better, and I tend to think that, but in both cases we can see that it generally adheres to that vague concept of what community should be in a network. There's a number of different ways to evaluate communities. There's various goodness metrics that we can use to evaluate the structural properties, and we'll go over a couple. For instance, density looks at the number of internal edges in a group of nodes. Now, this is not strictly for community detection. You may see this metric in various areas of graph analytics, but it's also obviously useful for communities because ideally each community would have a high density. Conductance looks at the total edge volume that points outside the community, and communities are sometimes called clusters. So this takes into account both the internal edge density and the outgoing edge density. And in this case, because with community detection we want there to be few edges pointing out of the community to other different communities, the lower this value is, the better. The value of 0 would be ideal because we want the community to be disconnected from the rest of the graph. And then finally, there's modularity, and that's really the focus of this video. And here, modularity is looking at the difference of the number of edges in a community and the expected number of edges. Now, the expected number of edges depends on what assumptions you're making, but in traditional modularity, the assumption is that you have an identical degree distribution. So given the current degree distribution of the network, does that community have more edges than expected? If so, that's good. If not, that's not so good. So just as a warm-up, let's look at some of the metrics before we get to modularity. Here we're looking at density. Again, this is a measure of the internal connectivity. Here's the equation for density. The density D of a group of nodes, S, is given by 2 times the number of edges between those nodes, divided by the size of S times the size of S minus 1. And really what this is looking at, this evaluates to the fraction of edges that exist between all these nodes out of the total number of edges that could exist. So for instance, in this example graph here we have 4 nodes. The total number of edges that could exist between these four nodes in an undirected graph, and here we're always talking about undirected graphs, is 4 choose 2, and that's going to be 4 times 3 divided by 2. So if you look at this equation, the denominator is the 4 times 3. The division by 2, since it was dividing, the denominator got popped up to the numerator. And so here we can see we have a value of 10 over 12. So that's pretty good. It's only missing one other edge that could exist, which would be between 2 and 4. So this is a dense subgraph. Let's look at conductance on the same example graph. And again, conductance is a measure of the internal and external connectivity. It's a fraction of edges pointing outside a community. The equation is given here. O sub s is going to be the number of edges pointing out of the community, and that's going to be divided by the total edge volume, which is the number of edges pointing outside the community, and 2 times the internal ones. And in this case, that gives us 3 over 13. And remember that for conductance, in terms of community detection, the lower the better. 3 over 13 is pretty small, but it's, could be better, right? In this example graph, we have 3 edges pointing outside the community, and there's only 4 nodes. However, the internal density, as we saw, is pretty good, so that makes the conductance better overall as it scales the denominator higher. Alright, so let's talk about modularity. Modularity is a global metric, and it's defined per network given a set of communities. Now this is unlike the last 2 metrics we looked at. For instance, with density, you can get the density of each community, so every single community will have some density. Same with conductance, each community will have a conductance. However, there's just one modularity value for the entire network given the set of communities. It's going to be a measure of internal and external connectivity, and it's looking at how well the network partitions in the modules. And in this case, the higher values are better. So let's take a look at the equation, which is given below, and we'll explain some of the terms. So modularity is usually given by the letter Q. That seems to be the most common. And again, it's going to be defined for a set of communities, which I have in the script C. The first term is just normalizing by the sum of the degrees. So you can kind of ignore that for now. Then there's going to be this main summation, which is going to be for every pair of vertices in the graph. So even if you have 2 of the same vertices, it's going to be every single pair, every combination. So what this is going to sum up is the following. It's going to be whether the 2 nodes are connected. This is a 1 or a 0. So this is a term for the adjacency matrix between node U and V. So that's going to be a 1 or a 0. And then you're going to subtract from that the 2 degrees multiplied by each other. So degree of U times degree of V divided by 2 times the number of edges. Finally, this term out here is called the Kronecker delta function, and it's going to be a value of 1 if the nodes are in the same community. Otherwise, it's going to be a 0. In other words, this term is going to be applied only for pairs of nodes that are in the same community. If they're in different communities, then it's going to give you a value of 0 regardless of what's in here. Now let's look at an example of this equation applied for every pair of vertices. so we can get an actual modularity value. And we're going to use this example graph here at the top right. So in this example, we have 4 nodes, 4 edges, and 2 communities. Nodes 1, 2, 3 are in one community, and node 4 is in its own community. And here is the complete step of the modularity calculation for this network and that community partition. Now remember, this summation is over every pair of vertices. So I've labeled each line here to show which vertex we're looking at. So for instance, this line here is everything for vertex corresponding to U. So this is going to be the term for vertex U equals 1 and V equals 1. This here will be the term for U equals 1 and V equals 3. Down here we have the term for U equals 3, V equals 2. So maybe we'll just look at one of these terms. Here, we'll do the one I was just at. So U equals 3 and V equals 2. So again, this term here is going to be this term from the equation, or these terms from the equation. So first, AUV is going to be 1. We have a 1 here because vertex 3 and vertex 2 are connected. They're adjacent to each other. The degree of vertex 3 is 3. That's why we have, and the degree of vertex 2 is 2, so we have 3 times 2. And then that divides by 8, because that's 2 times the number of edges. And since these two vertices are in the same community, we get a multiplication by 1. So the Kronecker delta function evaluates to 1. You can see some of these terms, that function is 0 because the pair of vertices are not in the same community. So for instance, vertex 4 and vertex 2 are not in the same community, so this all will evaluate to 0 because that delta function is 0. And in fact, since vertex 4 is in its community with itself and nobody else, all of these will be 0 except for the last one where it's looking at itself, so U equals 4 and V equals 4. So ultimately, if you add all this up, you get a modularity value of negative 0.03. If we look at the modularity of the original communities we were looking at, now we can answer this question: which is better, 3 communities or 2 communities? Well, objectively, at least now we can say that if you have these 3 communities here, you have a modularity score of 0.5. And if you have these 2 communities, you have a modularity score of 0.365. So now, rather than our personal opinion, we can say, well, the modularity of this is better. Alright, let's talk about some modularity values and what they mean. So first, modularity is bounded in the range of negative 0.5 to 1. So the best case is your communities give you modularity value 1. The worst case is negative 0.5. Now, an example of how you can hit those bounds is if you look at a bipartite graph and you put all of one partite in a community and all of the other in a different community, you can see that's sort of a very bad case because there's no edges between nodes in the same community, but there's a lot of edges pointing out. And if you look at the modularity of this graph, you'll see it's negative 0.5. In terms of the upper bound, if you look at a case where you have a bunch of cliques or completely connected graphs, and here I just have 3 cliques, but it could be 4 cliques, 5 cliques, whatever size cliques, and then you have a minimal connection between them. And each clique is going to be its own community. That's sort of a best case scenario. Because you have very few connections between communities, but a super highly connected community. And there's a paper that talks about this, but as the number of cliques increases, your modularity value converges to 1 because it equals to 1 minus 1 over the number of cliques. Okay, next, if you have all nodes in a single community or all nodes in their own community, that gives you a modularity value of 0. And that's simple to calculate. Non-zero values represent deviations from randomness. So a modularity score of 0 means that the community structure is no better than a random deviation. A negative value means it's worse, and then a positive value means you have more links than are expected. A quote from a paper says that in practice, if the value is about 0.3, it's a good indicator of significant community structure. And then there's other interesting properties that are listed in this reference if you want to view that on your own. Okay, so now I'm going to introduce another form of the modularity equation. So this is another popular form of the equation that you may see, and it evaluates to exactly the same thing that the other equation evaluates to. And here what we have is, rather than a summation over every pair of vertices, we have a summation over each community in the set of communities. And we're going to add stuff up. So here, E of C is going to be the number of edges in that community. E is going to be the total number of edges in the graph. From that, we're going to subtract the sum of the degrees of the vertices in the community divided by 2 times the number of edges, and that term will be squared. So if you evaluate this equation, it'll exactly match the other one. They're equivalent. And why are they equivalent? Let's take a look at a derivation. So on the left here is the original equation I introduced. And on the right is a new form. So again, on the left we're doing summations over every pair of vertices. On the right we're doing a summation over each community. So take this first term here. We're looking at the number of edges in the community. That's equivalent to the first term in the original equation. Now remember, because these are summations, we can split up these two different terms into individual summations. So for instance, if we look at the first half of the summation, this term will be a 1 or a 0 depending if U or V are connected, and that's only going to be evaluated because of this delta function on pairs of nodes that are in the same community. If they're not in the same community, it'd be 0. So really what this is doing is it's summing up all the edges in a community by a factor of 2. And it's by a factor of 2 because we look at both UV and we look at VU. So we're going to sum a particular edge twice. And if you keep this normalization term here, then we end up getting exactly this corresponding term of the other equation. Now let's consider the second half. So here we're summing up the degrees of the community, and again we have some kind of normalization. Well, if we look at the original equation, we have degree of u times degree of v times this delta function. So really what's happening here is for every pair of uv we have degree u times degree v, only if they're in the same community. Now if you factor this out, you end up getting the sum of the degrees squared, which is exactly this here. And then again, if you maintain this normalization term, that's where the 2e comes from in the denominator of the other equation. Now you'll sometimes see this form of the equation in papers or code because it's a bit simpler to compute or think about because you're looping over the communities rather than every pair of nodes, even though you're getting the same value. So if you look at NetworkX, which is a popular graph analytic library written in Python, it has a modularity function that you can use to calculate modularity. And we can see how they implemented it. So if you look at this code, you'll notice that there's different code paths depending if the graph is directed or not directed or weighted. So we haven't talked about those things yet, so just ignore it. So ignore the directed version and just look at the undirected version. Here it's collecting some terms, so it's setting m equal to the degree sum divided by 2. So really that's going to equal the number of edges in the graph. And it's setting up this normalization term, which is 1 over the sum of the degrees squared. So if we look at the main function now, we have some community. L sub c is summing the weight. In this case we don't have weights, these are just adjacencies, either 1 or 0. For u and v in the set of edges of that community. So what this term is here corresponds to this e of c in the equation above. It's going to be the number of edges in the community. Then it's getting the out degree and the in degree, which is just going to be the degree of a vertex if it's not a directed graph. And then it's simply returning that. So it's doing L sub c over m, which is this term here. And then you can see, ignore this resolution term for now, we'll talk about that later, but the out degree times the in degree times the norm. Now this looks a little different than our equation, but what you'll see here is that in degree and out degree are the same if it's not directed. So really that's the square of the degree, and the norm, as I mentioned before, already has a square term in it. Let's talk about some of the intuition behind the equation. So the idea is we want to reward links within communities and penalize missing links within communities. So one way we can think about that is developing this generic equation here, h. And what we do is, if there's a link in a community between two nodes, I and j, that's a positive value with some weight. And if there's a link that doesn't exist between two nodes in a community, that's going to be a negative value with some weight. If we look at every pair of nodes and all this evaluates to a good positive value, that's good. If it's a negative value, that's bad. So the question is, how do we want to decide to handle these weights? And there's multiple different ways you could do it, but one way you could think about doing it is based on the probability of a link between I and j existing. So you could say that B we're going to make equal to the probability that a link between I and j should exist, and then A is going to be 1 minus that probability. In other words, the probability of no link between I and j. So if the probability of no link between I and j is high, that will reward there being a link between I and j. And if there should be a link between I and j, but there's not a link, that'll hurt us. And if we simply plug this into the equation above, we can simplify it to look like this. So what should be the value of Pij? What should be the probability of a link between I and j? Well, one way you can get that probability is based on degree distributions. So you can think of it like this. Take every link in the graph that exists and cut it. So you have a stub for every link. So this would form two stubs, one stub off I and one stub off j. Now if we think about the probability of one of the stubs of I connecting to one of the stubs of j, then we have 5 choices, because I has a degree of 5, 1, 2, 3, 4, 5, by 4 choices, because j is a degree of 4, 1, 2, 3, 4. So any of these links could connect to any of j's links. At the same time, any of these links could connect to any of the links in the rest of the graph for any of the other nodes. So the probability that it'll connect specifically to j is going to be 5 times 4 divided by all the other choices it could be, which is 2 times the number of edges. 2 because we've cut the links to get 2 stubs out of each link. And that's where we get this equation here. And now this should look very familiar, because if you plug this term into here, what you'll notice is that that's the equation of modularity. Now modularity can be naturally extended to directed and weighted graphs. So for a weighted graph, rather than the adjacency matrix, which would give you a value of 1 or 0, you now have this weight matrix, which is just going to be the weight of the edge between u and v. And then you're going to have the weighted degrees, and instead of the number of edges, you're going to look at the total weight of the edges of the graph. For directed, you're going to have directionality incorporated. So the adjacency matrix is going to be now based on outgoing edges, which is what this O is for. And the degrees are going to be based on outgoing links and incoming links. Now the intuition behind that is that if you have an edge from a node with a high outgoing degree to a node with a high incoming degree, then that's expected. If you have an edge from a node with a low outgoing degree to a node with a low incoming degree, then that's unexpected. And then also for the directed case, your normalization terms are going to lose that constant 2 that you see in the denominator above. Now, modularity isn't the perfect solution. This doesn't mean that just because the modularity says something is good, that it is good, that it's a truly objective metric, because it's not. Remember that there is no formal definition of what communities in a network are. Modularity is just one metric you can look at to help evaluate. Some issues are that this thing called the resolution limit, which comes from the fact that we're using a model that assumes edges could be randomly attached to any other edge in the network. What can happen is that in a large network, even a very weak connection between groups of nodes could be a sign of a strong correlation, simply because the denominator becomes so large, because we have so many edges. What this can do is bias towards large communities. And again, this is called the resolution limit issue. One way you can address this is by a weighting factor on the importance of this probability. So this is usually given by lambda. And so a value of 1 obviously would do nothing. A value of greater than 1 puts a higher importance on this term, which means that the number of edges in your community must be much greater than expected. So if you have a value of 2, that means the number of edges in your community must be greater than 2 times the number of expected edges. Otherwise, you'd have a negative value. It's not really useful in simply calculating the modularity metric. Where it gets useful is if your community detection method looks to optimize modularity. So you look to find communities by trying to partition nodes that will optimize this value, and then this factor becomes more important, and it can help you specify the granularity of what you're finding. So a higher value may lead you to smaller communities, and a smaller value will lead you to larger communities. This is just some of the references I use throughout the presentation, and they are useful papers or links to code, which may be good to look at for further reference.